Okay, so here we're going to take a look at some common vector spaces. So I'll describe what the sets are briefly and maybe go over a property or two of these, uh, but we won't go through the whole process of verifying all 10 of those axioms that we've laid out before. Just know that they do follow the 10 axioms. Now the first one are the set of column vectors, right, from our Euclidean M space. Okay, now for our vectors, our column vectors, we defined what equality was, right? If we had some u, right, whereas u1 through um, v1 through vm, right? And we defined what equality was, right? Where element-wise, they had to be that u1 must equal v1, u2 must equal v2, etc., for them to be considered equals. And we defined the what it meant to add them, right, element-wise, and what scalar multiplication was, right? So those operations were defined for our Euclidean M space, and we saw that it does follow all those properties here. Right, so that's one vector space we've seen already. We've also seen the matrices of n by m or m by n, right? So here, right, we know what it means for two matrices to be equal. So entry-wise, the elements are equal to each other. In order for two matrices, all of them need to be equal to each other. In order for two matrices to be equal to each other, we also define what it meant to add two matrices, right, where we add first element in the first row, first column, plus first row, first column, etc. Right? And again, we went through and when we started talking about matrices, the theorem, believe VS vector space properties for matrices. It goes through verifying all those 10 properties here. All right. So now in the more general sense, when we have m by n, since it is a vector space, I will refer to them as vector u, even though again in this space that vector u looks like a matrix, right? Because it is a matrix. Okay, but again, in a more abstract form, it belongs to a vector space, so the elements, the objects in there, are considered vectors. Okay, so these two we've seen before, right? Now, one that we haven't seen before in this context, in this class, but you probably have worked with extensively in your calculus courses, is polynomials. So here, this P sub n are polynomials It's a set of polynomials of degree at most n with, again, real coefficients. For our sake, I just deal with the real coefficients. Again, the textbook goes into complex for coefficients, but we won't worry about those. Okay, so for example, something like P3 would be all types of polynomials that are that looks something like this: a0 plus a1x plus a2 x squared plus a3 x3, such that a1, a2, a3 are elements of real numbers. Right, now some of them may be zero, like for example, elements here could be like, it could be, right, cubic degree 3. It could be also x squared minus x. Right, it could be also 0. Right, those are elements of P3. All right, now what does it mean to add, or what does it mean for two polynomials to be equal? Well, each of the coefficients for the, so if I said that this, what does equality mean for this polynomial? right? So it means that A0 equals B0, A1 equals B1, A2 equals B2, and then A3 equals to B3. Okay? And in general, if we're working with, let's just keep it Pn, right? How do I define addition, right? So addition, standard addition, if we have vectors here, that's one vector u, and then our other one, b0, b1, x. Well, what would it mean for this operation u plus v? What is the algebraic operation that we're used to having here, where what we do is, right, that idea of combining like terms. Right, so what that means is we would combine this like that, right? And that's how we would define, again, to define the addition here. All right, and then scalar multiplications, right? Scalar multiplication, we would define something like alpha u, right, to be alpha across a0, a1x, a sub n, x to the n, right? But just distributing here, right, we multiply the scalar by each one of the coefficients. Okay, so now we could see here the polynomial of degree at most n, or p sub n, that is also going to be a vector space. All right. Now, these elements don't necessarily need to be finite. So what I mean by that is we can also define the vector space of infinite sequences. Right? Not column vectors, but a sequence here. So a sequence just would look like C1, C2, C sub 0, C sub 1, C2, etc. Right? Such that C sub i's are just some real numbers. All right, so this set is all of these infinite sequences. And as we can see, we can say, what does it mean for a sequence to be equal, right? If u equals to v, right, where their element of my vector space here are to infinity, well, it would mean here that if I say these two are equal, right, what that would mean is that, again, element-wise, c sub I will equal to d sub I for all I greater than or equal to 1, or excuse me, 0. Okay? Okay. And then we can define addition, again, element-wise, right, similar to the column vectors. The only thing here is that these are infinite sequences. All right, and one last kind of vector space is the vector space of functions. We have some function f from our domain x onto, again, just worried about real valued functions here. So this forms a vector space with our, again, excuse me. What does it mean to add? Well, it's the common definition that we have of thinking about multiplication of, or excuse me, addition of functions, right? So here, Right? We've defined kind of an algebra class. We define what it meant to add two fractions and to have the scalar multiple of our function. Right, so those are the definitions. Now, again, equality, right, depending on what the function looks like, right, it has to be the exact same type of function, the mapping from x onto the real numbers. Okay, so that is also a vector space. All right, now we seen here again different vector spaces, but in each case I'm using the same notation to refer to the objects, like the vector u, right? The same addition symbol. It just kind of depended again on what space I'm in, what that means, how I interpret that. Okay, so later we'll see just some oddly defined vector spaces where we specify what it means to add, right, and how that can also be a vector space with the proper definition.